All right, welcome. Today, we're going to tackle Thevenin's theorem. Now, this is a super powerful tool that lets us take a really messy, complicated-looking circuit and boil it down to something so simple you'll wonder how you ever lived without it. So, let's just jump right in.
So here's our roadmap for today. First, we'll talk about why complex circuits can be such a pain. Then, we'll introduce Thevenin's theorem, this really elegant solution. I'll show you the simple two-step method to actually use it. We'll uncover why it's so powerful, and then we'll wrap up with the key rules you've absolutely got to remember.
Okay, first things first. Let's talk about a problem that, every single person who's ever tinkered with electronics eventually runs into.
Okay, so just picture this. You're staring at a circuit diagram, and it looks like a total mess, right? You've got multiple power sources, you've got resistors scattered all over the place. It's the kind of thing that can really make your head spin.
But here's the real question. What if you only care about what's happening to one little component in that entire jungle of a circuit? Do you really have to solve the whole thing, write a dozen equations just to figure out what's going on with that one piece? Well, that sounds like a ton of work, and frankly, it is. But thankfully, there's a much smarter way to do this.
And that brings us to the hero of our story today, a French engineer named Léon Charles Thevenin. Way back in the 1880s, he came up with this absolutely brilliant shortcut that makes even the scariest-looking circuits way simpler.
And here it is, the big idea. Thevenin's theorem basically says you can take any complex linear circuit and from the point of view of any two terminals, you can replace the whole thing with just one voltage source and one resistor in series. That's it. It's kind of like a magic trick for circuits. And this really shows it all. You're going from that tangled mess on the left to this beautifully simple, elegant equivalent on the right. And you know the best part? The component that you're interested in, it literally can't tell the difference. To that one little part, the simple circuit behaves exactly the same as the complicated one. Okay, so how do we actually do this? How do we figure out the right values for that voltage and that resistance in our new simple circuit? Well, it's actually a pretty straightforward two-step process. We just need to find two things: the Thevenin voltage, which we call VTH, and the Thevenin resistance, or RTH. As soon as we have those two values, we're done. We've built our equivalent circuit. So let's break down how we get each one. All right, step one is finding VTH, the Thevenin voltage. It's actually pretty simple. It's just the voltage you would measure across the 2 points where your component used to be after you've taken it out. You can just think of it as the open circuit voltage. And next up, we've got RTH, the Thevenin resistance. This is the total resistance of the circuit looking back from those same 2 points. But, and this is the important part, you have to turn off all the independent power sources first.
So, what does turning off a power source actually mean? Well, it's about neutralizing its effect on the circuit's resistance. For a voltage source, that means you make its voltage zero, which is basically the same as replacing it with a plain old wire or a short circuit. And for a current source, you make its current zero. No current means there's a gap, so you replace it with an open circuit. Getting this right is absolutely crucial for finding the correct R Thevenin.
Okay, so we've done the work. We've found our V Thevenin and our R Thevenin, and we've built this new super simple equivalent circuit. So now what? Well, this is where the real power of this whole technique kicks in.
This quote really nails it. Your little component, the one you care about, it has no idea it's connected to a simple circuit instead of that original complex beast. And this is huge, because it means you can now try out different components, say different load resistors, without having to resolve that entire complicated circuit every single time. It's a massive time saver.
But wait, there is more. This simple little circuit also unlocks another really important concept called the maximum power transfer theorem. It's a fancy name, but it answers a simple question. How do you get the absolute most power out of your circuit and into your load?
And the answer is just beautiful in its simplicity. You get the maximum possible power delivered to your load when the load's resistance is exactly equal to the Thevenin resistance of the circuit that's feeding it. When those two match, bam, you've hit the sweet spot for power.
All right, let's wrap this up. We're going to go over the most important things that you should take away from this whole explainer on Thevenin's theorem. Okay, let's lock in these key points. First, and this is a big one, this whole trick only works for linear circuits. Can't stress that enough. Second, its main job is to make your life easier when you only care about what's happening to one part of a bigger network. And remember our two magic numbers. VTH is the voltage across the open terminals, and RTH is the resistance you see when all the sources are turned off. And finally, remember that this simple equivalent is your secret weapon for figuring out maximum power transfer.
So there you have it, Thevenin's theorem. It's so much more than just a formula, right? It's a whole new way of thinking, a tool for seeing the simplicity hidden inside of all that complexity. So, the next time you see a circuit diagram that looks like a total nightmare, you'll know exactly what to do. You'll know how to find its simple, elegant heart. Thanks for joining me on this one.